All right. Well, look, thanks very, very much for the invitation to present this material and to imagine I'm in LA, even though it's my spare bedroom, like everybody else. Today I'm going to be talking about the background approach and how to exhaust it, or basically how to use it or push it as far as possible to try and lower the upper bound on the Nusselt number in Rayleigh Benard convection. So really, this is a continuation or fits with the talks on Monday that we heard. So I won't labour the introduction too much here because it's clear what the situation is. I think we've heard a number of Rayleigh Benard convection talks. I'm thinking about two layers which are parallel, a distance h apart. There's a hot plate on the bottom, cold plate on the top. Temperature difference, which is measured non-dimensionally by the Rayleigh number. Sigma is my Prandtl number. I've noticed that I'm a little bit out of kilter. Everybody else uses PR, but sigma is my Prandtl number here. And I'm interested in this quantity that a lot of people have been talking about, the Nusselt number, which is the ratio of the total heat flux with the conductive heat flux. And what we're hoping is that there is some simple scaling law as the Rayleigh number goes to infinity. And I've basically suppressed any Prandtl number dependence. I'm not going to talk about that in this talk, and it's actually not, as far as I can tell, very significant. Contrary to what's shown on this diagram, I'm going to be talking about stress-free boundary conditions on the velocity field rather than non-slip, which is shown here. Okay, so just a very simple overview of the sort of results out there on the Nusselt number. As Basil Galeg introduced us to on Monday, there's something called the ultimate regime, which is based on mixing length theory, basically. Goes back to Kreiknen and Spiegel in the 60s. And this has the Nusselt number going as Rayleigh to the half. Then there's the classical regime, where the Nusselt number goes as Rayleigh to the third. And this is based on a number of different types of theory, rather nice theory by Priestley and Howard. Howard's theory based a lot on Marcus's ideas in 1954. And I think it's probably fair to say that the jury is still out on whether experiments show the ultimate regime, at least with solid boundaries and Dirichlet conditions. And so I think most people are beginning to think that the heat flux might scale as the Rayleigh number to the third. But if you have any spare time, you might like to look at lots of the comments that are appearing in the literature with people talking about each other's experiments, either in the laboratory or numerically. Okay, so what do I want to do? Well, I want to take some upper bound calculations which were done in 1996 using a new technique called the background method and try and lower the bound that comes out of that approach. At the moment, it produces the ultimate scaling of Rayleigh to the half. And of course, if one believes that experiments and numerics are really showing Rayleigh to the third, there's a huge gap in the exponent that we'd like to try and get rid of. And so the obvious thing to do is to add more dynamical constraints to the upper bounding calculations and to see if that will have the effect. Now, I put in inverted commas, add more constraints, because this is much more easily said than done. Anyway, I want to try it here. Before I go on to do that, I want to just give one more motivation for this calculation I'm going to talk about in a moment, and that is right at the bottom, WALF 2015. We've already heard about these calculations, and these are simple, well, I say simple, clever numerical computations where the 2D roll solutions, which bifurcate off in the classic way at 1708, are continued up to very large Rayleigh number, and with a view to actually looking at the Nusselt number associated with those rolls. And it turns out that the Nusselt number, if you don't optimize over the domain or the aspect ratio of the rolls, behaves like Rayleigh to the 0.28. Whereas if you optimize over the aspect ratio of the rolls, you can actually get Rayleigh to the 0.31. And of course, in 2015, I think most people were speculating that this experiment was really a third. And in fact, recently, we heard on Monday with David Goloskin, further computations have actually confirmed, I think, that this scaling goes as Rayleigh to the third. So this then opens the question, and in fact, this plot down here is what David showed. This is a sort of up-to-date compensated plot for the Nusselt over Rayleigh number to the third. So it really does beg the question, could 2D rolls actually be an upper bound on the data? So if you look, all this data here is below this corresponding line once it's been compensated. So that was the second motivation for looking to try and extend the background approach. So the key questions are, can the upper bound be lowered from the ultimate to the classical scaling by incorporating more constraints? And the second question, which was really the one that motivated me 2 or 3 years ago, is if you were successful enough to include all the steady dynamical constraints, could the optimal be a steady Boussinesq solution? And in particular, could that steady Boussinesq solution just be this 2D steady rolls that Wall F found? Okay, so how am I going to address this? Well, I wanted to take the simplest possible system, and that is 2D Rayleigh Benard convection with stress-free boundary conditions. And there was a second motivation for looking at this system in that it's been extensively treated now using what's become known as the wall-to-wall problem or approach. And that goes back to Hasan Zaydar in 2014. And Ian Tabasco talked about this on Monday too, where you impose the full heat equation, but not much else to try and bound a Nusselt number. Well, what I wanted to do was take the background approach and do the same thing, i.e. impose the full heat equation in this particular configuration. So far, the background approach has only been used where a horizontal average of the heat equation has been imposed. So that was the big thing, to try and open up that constraint and lower the bound. Okay, so let me just give you an idea of the background approach before I give my main result. Here are the Boussinesq equations. Again, remember that sigma is my Prandtl number. There's the Rayleigh number in there, momentum and heat. And the background approach sets up a Lagrangian here, where grad T squared is basically the Nusselt number. And then I introduce some dynamical constraints here, the momentum and the heat. And the red underlined quantities are the Lagrange multipliers, and the N and the H are the equations that I've listed above. Now, the background approach is rather interesting in the sense that you don't stop here. What you do is you link the Lagrange multipliers to the physical fields. And the question, well, the key feature is of how close you link them determines what dynamical constraints you actually are able to impose in the calculation. So underneath, I've just linked the nu, which imposes the momentum equation with the velocity field u. So that's a direct link, and then as a consequence, all I impose is the power later on, just the u dot momentum equation integral. Whereas if I link the Lagrange multiplier for the heat equation theta with the physical temperature and allow a little bit of wiggle room here in terms of this background field Tor, then I can impose further constraints from the heat equation. And you can see it underneath that if I substitute this expansion of theta into the Lagrangian, I get these three constraints. I get the power, I get an entropy, and then I get this last term, which is imposing the heat equation, as long as Tor has dependence on X and Z. Now, so far in applications of the background method, Tor has only been allowed to have dependence in Z. And so this last constraint has just been a horizontally averaged heat equation. But by retaining the dependence in X, because my domain is X and Z, then I'm actually imposing the full heat equation here. Okay, so if I go back to this new expansion in nu and theta, rewrite the whole Lagrangian in terms of tau, u, and theta, I get this expression where I've dropped a few numerical coefficients just to make it cleaner. And this is the crucial realization of the background approach, that I can split the dependence in the Lagrangian between tau, which is this positive definite quantity here, and the quantities I don't know anything about, the velocity field and the temperature field over on the right-hand side in this g function. Now, something I haven't emphasized so far is I have choice as to how I choose tau. All it has to do is satisfy the boundary conditions, but otherwise, I'm allowed to choose tau as I like, because I also don't know what t is. All right? So all the unknowns in this expression for the Lagrangian are u and theta, and they're contained in this g function here, or functional underneath, where I've indicated here. Now, crucially, the terms with red line underneath are positive definite, whereas the term which is green is positive sign indeterminate. And the procedure at this point is to choose tau such that g has a minimum. Now, the minimum of g, if it exists, is 0. That's what I'm interested in. Obviously, I don't want minus infinity because I'll have no bound. But if I specialize to the case where min g is 0, I similarly have two possibilities. The velocity and temperature field can either be 0, or the velocity and temperature field can be non-trivial, and these are marginal modes. And these are the important things that you need to find. Because if you think about going back to this Lagrangian up here, if I take the variational derivative with respect to tau, and I want to get a non-trivial equation, I must have a non-trivial u and theta here to get this term. And this is really the crucial thing. Once I've got that g has a minimum, I can look at all the relevant tau that allow me to then minimize this first term. So the problem becomes a min-max problem. Maximization of u and theta, well, that's basically finding g equals 0, such that I then minimize over all of those tau that have this maximum. Okay, well, it all actually boils down to this spectral problem here. And this is the crucial thing. This is basically the spectral constraint. And what I need to do is find marginal modes which satisfy this as a function of tau. Now, the crucial thing is, if tau just depends on z, this eigenfunction partitions when I do a Fourier decomposition into eigenfunctions for each wave number in the x direction. And that's nice because I can do a simpler problem in 1D many times. And the crucial thing is that the marginal modes are then Fourier modes in x. And I can add them all together to give me an optimal solution. This is the optimal solution that you'd write down. It's just all the Fourier modes, which are marginal, such that they're non-trivial and produce g equals 0. Okay, so there's a further simplification here too, in that this g is also just simply the sum of the g's of the individual Fourier modes. And this is crucial because what it tells me is if I do the variation of the gj's with respect to the individual Fourier modes, and I set those all to 0, it's exactly the same as taking the variation of the full g with respect to my composite velocity field, in other words, this optimal field here. So what this tells me is the optimal will satisfy the constraining equations, which is no big deal. You'd expect that. So here is my minimum problem over a maximum in u theta. My dynamical constraints are satisfied at the stationary point, and that's where my optimal is. Now the contrast is if I extend tau to be two-dimensional, then my eigenspectral problem does not separate, it's fully 2D in X and Z. And so when I come to write down the modes, which are marginal, they're also going to be a function of X and Z. Now, if I write down a velocity field, an optimal velocity field, which is just a sum of these marginal modes, then the key thing is that when I substitute these into G as a composite field, and I've written it here, this is now not the sum of the individual GJs, where I put in the individual marginal modes into G. So at this point, I'm no longer assured of the fact that if I take variations of GJ and they all vanish, that the variations of the composite G will also vanish for the optimal field defined up here. Now that sounds a little bit esoteric, but what it means is that the optimal, as defined here, does not satisfy the constraining equations. So in other words, the conditions that I'll essentially have to satisfy using this spectral constraint will move the optimal away from the saddle point position here. So the dynamical constraints are satisfied at this saddle point, but the solution of my optimal problem will be away from that saddle. And this is crucial because now what it's saying is that the solution of the optimal problem will not be a solution of the dynamical constraints I'm imposing, because I have to essentially have this spectral constraint too, and that moves me away from this stationary point. And before I go, I should say that Andre Souza, Ian Tabasco, and Charlie have also written a paper which is very complementary to our calculations. And Andre has actually concocted a nice example of this, very simple example of how this happens. Of course, I'm dealing with a PDE problem here. He's got a much simpler canonical problem. Okay, so let me, after that point, go back to the comparison with Hazen-Zadar. So Hazen-Zadar's Nusselt number versus Rayleigh number plot looks like this. They've got the black dots, and they find a scaling of Rayleigh number to the 5/12. We can reproduce that with one wave, so one spectral marginal mode, but you can find 2-wave and 3-wave bifurcations, which is entirely typical here. Let me just emphasize that these waves are fully 2D fields. And as soon as I move away from the 1-wave problem here, then the background optimal is moved away from the saddle point. So in other words, these solutions have lost connection to the dynamical equations rather remarkably. And what we find in the same configuration as Hazen-Zadar is if you carry on these waves to a higher wave number, you'll find that they start to approach Rayleigh number to the half. Now there's another feature of the Hazen-Zadar problem in that they, for numerical reasons, introduced a plane of symmetry. And it turns out this plane of symmetry is crucial. If you do the 2D heat equation calculation of the background profile, you'll find that the background profile is really 2D because of this line of symmetry. But as you gradually open up the domain and make it larger and larger, this line of symmetry becomes less and less important, and you can start to see the 2D background field wanting to become 1D. And in fact, there's a result due to the fact that the problem in the infinite domain is convex, that you anticipate the background field really is one-dimensional. So what this is just saying is that even with the heat equation added, you do not improve the bound because of the fact that you actually do want to come back to a 1D field. If you're in a finite domain, then you have to have a 2D background field. But for the idealized theoretical model where you have an infinite domain, the 1D background field is optimal. Now, so far I've just talked about the heat equation and adding the full version of that. We also tried adding a background velocity field. So in the top half of this overhead This is the configuration, or this is the decomposition we used for the first part of the talk. Now I want to generalize it even more and have this degeneracy between the velocity field and the Lagrange multiplier for the momentum equation, this phi. Now the problem is non-convex, and it's completely not clear whether this is going to help. So what we managed to do is an inductive bifurcation analysis, where essentially when these wave numbers come in, these new marginal modes come in and make the optimal solution more and more complicated, we tried to establish that if phi is 0 before the bifurcation, which is what's always assumed in the calculation so far, then you can show that phi has to equal 0 afterwards. So essentially, as you go along these bifurcations, which I've tried to indicate here on the right-hand side, you can check to see if there's a condition for this phi to be non-zero. And each time, phi has to be 0 by a solvability condition. So the net result of all this is that extending definitions of the background fields in the background method does not improve the bound, unfortunately. This is definitely true for temperature and probably true for velocity. Of course, there could be branches in the upper bound problem which are not smoothly connected to the initial bifurcation point, in which case our inductive proof will not capture that. So the bottom line is that this bound here, which was calculated by Steve Plasting in 2003, is actually still the best bound out there, even after 17 years of trying. And getting back to whether the steady solution of the equations can be an optimal, well, it certainly can't be for a background problem because of this lifting off the saddle point due to the spectral constraint. And the background method, as I've briefly described here in 2D, confirms Hazen-Zadar for a Rayleigh number of less than 4468. But beyond the situation where multiple wave numbers come in, the situation is unclear because, as I say, the background method lifts off the stationary point, which is what Hazen-Zadar are trying to find. And I'll stop there. Happy to take questions.